After working as a postdoctoral fellow at KHU from 2019 to 2020 and at the Korea Institute of Science and Technology for 1 year, he joined KHU as a research professor from 21 to 22. That same year, Junaid joined the Interdisciplinary Center for Security, Reliability and Trust, SnT, at the University of Luxembourg, where he is currently a research scientist in the Signal Processing and Communications Group. Junaid also served as a technical program committee member of multiple IEEE conferences, including the International Conference on Communications and the Global Communications Conference. Today, Junaid is going to talk about one of his research interests, namely the purpose of quantum communication. And he will offer us an overview of the infrastructure related thereto and what is being done in Luxembourg in this field. Junaid, would you please join me on stage?
Thank you very much for the kind introduction. Okay, I'm going to introduce Luxembourgish National Testbed for Quantum Communication Infrastructure that we are building at University of Luxembourg. This is the agenda of my presentation. It is divided into 3 brief sections. The first one is the motivation. I'm going to talk about why we need quantum communication systems. Then I'm going to move into what we are going on national level. And finally, I will invite all of you to get involved, and we will talk about how you can get involved in the whole procedure. So, to start with the motivation of quantum communications, let me ask you a simple question. How many of you can solve this integral to get access to Wi-Fi if you are given, let's say, 5 minutes? Oh, there is one hand. Okay, there are maybe 1 or 2 hands here in the hall. But based on this small number of hands, can I assume that the Wi-Fi that has this password is actually a secure network? I do not think so, because although this is a very small room, there are very few people here, but if you go outside, there will be thousands, or if you go to the global level, there will be hundreds of thousands of people who can solve. This is actually a very simple integral to solve. The answer is pi, by the way. So based on this assumption that if there is a select few number of people who cannot solve this integral, if I put some secret information behind this, this is not a very good way of securing my Wi-Fi. The information security that is implemented today, that works on a similar model. So we look at some very difficult computational problem that is not difficult only for humans, but also for very difficult to solve for computers as well. And then we somehow put all our secrets behind the solution of that problem. So the RSA algorithm, some of you might be familiar with that, is based on the factorization of very large prime numbers. So this RSA algorithm encrypts all your communication, for example, your emails, sometimes your banking details, and all other. This model of security is called complexity theoretic security. So you assume that this problem is very complicated, nobody can solve it, okay, this is good enough. But if there is some financial assets behind that, the best method for you would be to just solve the problem and then keep quiet. No, do not tell anyone, and then maybe keep on stealing pennies from everybody's account, and you will be a millionaire and nobody will know. Okay, so what is the alternative? We want to move from the complexity theoretic security. One of the alternative is not something new. It was actually formalized in 1949, and it was well known before that as well. This is one of the major works from Claude Shannon, the communication theory of secrecy systems. In this work, he formalized the notion of perfect secrecy. The perfect secrecy systems are the systems that do not take any assumption of the computational complexity of some problem. So regardless of the computational power that you have available at your hand, you will not be able to break this secrecy line. However, if this was known from 1949, why we do not have this yet? There are a few catches. The first one, you are going to encrypt your systems with some secret key, and there are very rigorous requirements, very strong requirements on that key. For example, the size of the encryption key must be same as the message. So if you want to transmit a video file of, let's say, 1 gigabytes over the internet, you will require a key of 1 gigabyte as well. And then there are some other technical requirements. I'm not going into detail of that. But then think about this. If you had some means of transmitting your secret key, why would you not send your file directly? Because if your system is secret or strong enough to transmit the secret keys, it should be strong enough to send the file as well as secretly. So if you talk about the current security system, the complexity theoretic security, you cannot transmit your secret keys without going beyond the assumption of the complexity theoretic security. Okay, so with these assumptions of on the key, how you are going to transmit your key. So this is what we are going to talk about. The quantum key distribution systems are the systems that transmit the secret keys with the guarantee of information theoretic security or the perfect secrecy. So that your key is not going to be intercepted. If it is intercepted, you will immediately know that. So the work process for quantum key distribution goes something like this. You have a quantum channel. This quantum channel can be any optical channel. It can be a fiber optic, or it can be free space optical channel. You have this quantum channel, and you have another classical channel available. So on quantum channel, you transmit your photons, you encode your information into quantum bits, and on classical channel, you communicate with each other between the transmitter and the receiver. You perform some checks on your key to make sure that your key was not intercepted. Once you are guaranteed that your key was secretly transmitted, you can use this key for your communication. So this is the very, very basic idea of quantum key distribution. They are not the communication systems. They only transmit your secret keys. So you cannot transmit your original data on this. So I'm going into details of what we are doing in the field of quantum communication at SnT. So we are building the national testbed. The national testbed is in the form of a quantum key distribution network. So we have multiple nodes. Two of our main nodes reside in the University of Luxembourg campus in Kirchberg and the University of Luxembourg campus in Belval. We have another cross-border connection planned with Belgium that will be available before the end of this year. The connection between the two nodes of the University of Luxembourg, it is currently working. And then we have 2 or 3 more connections within our network. So we have a very small topology, small number of nodes within our network, and this makes our national testbed, where you can come in, join us, experiment with the devices, and look at what are the challenges in quantum key distribution systems. This system is not mature enough to put into production, but this is as good as it goes for a national testbed. So talking about the challenges in quantum key distribution system, one property of quantum bits is that they cannot be copied. So if you think about it, it means that if you cannot copy, you cannot amplify as well. So the only communication you can do is one hop. So if you want to go beyond that, you cannot put an amplifier or a repeater in between, the traditional repeater in between to increase the distance towards which you can communicate. So this is one of the challenge. And then there are other challenges in the network design as well, how you connect all the nodes together, who knows what part of the key. So these are the all challenges that you can come join us and we can have a look at together. So how you can get involved? If you want to do some experimentation as a lab facility, you are welcome to join us. Come, we can discuss about it. If you want to do, you have some technology in mind based around the secrecy, based around the quantum key distribution, please come join us. We can have some technology validation in our lab. And also, if you are some researcher who wants to collaborate to do some projects around this idea of quantum key distribution. We are open to that as well. This is the partnership program of SnT. We try to work between the technology readiness level 2 to 6, because this is where we believe we can create the most impact. Beyond that, it is the industrial problem. Before that, it is very, very fundamental science. So we expect the collaboration to be between these TRL levels as well. Thank you very much. That is all from my side. Please scan this QR code if you want to send me an email and get in touch with me. Thank you very much.